You're back. Good. Let's talk about oxymercuration of triple bonds. All right, so we finished off the last video by saying hydroboration of a triple bond will give us a ketone if it's an internal alkyne, or if it's a terminal alkyne, it will give us an aldehyde where we put the carbonyl on the primary position because hydroboration is anti-Markovnikov. So what happens if we use oxymercuration? And this is not really oxymercuration, but there is mercury involved, so it's the closest thing we got. So we're going to use mercury sulfate, HgSO4. We're going to use H2SO4, sulfuric acid, and we're going to use water. And what we're going to get is the addition of water across a pi bond, right? We're going to get an enol out of this, and this is going to tautomerize. We're going to dance that hydrogen off of the oxygen and onto the carbon, and we're going to get a ketone. Right? Our pi bond goes and attacks H plus, creates a cation. The H2O comes in and attacks that cation. We make the enol. It tautomerizes to give us H plus. Stop me if you've heard this one before, right? It's the same mechanism as we've seen a whole bunch of times. All right, so for an internal alkyne, that's basically exactly the same thing as what we did on the previous slide, right? Internal alkyne, hydroboration gives us a ketone. Internal alkyne, oxymercuration gives us a ketone. Where the difference is of course the terminal alkyne, because now we have a choice between a primary carbon right here and a secondary carbon right here. So if you had to predict what is going to happen here, you would predict, right, that you're going to add the oxygen to the more substituted position. And that means that you're going to get the enol where the oxygen is on the secondary position, like this. That's going to tautomerize, because anytime we see an enol, we immediately tautomerize it to give us a ketone, right? And we've added, so this hydrogen goes from the oxygen where it's attached initially down to this carbon that was part of the alkene. So we end up with 3 hydrogens here. That's where the CH3 comes from. But we always get a ketone out of this. So the difference between hydroboration and oxymercuration is that in hydroboration, we add the oxygen to the terminal position, the primary position, and we end up with an aldehyde. In oxymercuration, we add it to the secondary position, the internal position, and we end up with a ketone with a CH3 group over here. So terminal alkynes give you different products if you use oxymercuration or hydroboration. So this is probably worth writing down. Terminal alkynes give us different products if we do oxymercuration, HgSO4, H2SO4, H2O. Right? We always add the oxygen to the secondary position, so we get a ketone. They give different products if we do hydroboration instead. So if we do C-borane, hydrogen peroxide, sodium hydroxide, and we would get the aldehyde. So terminal alkynes will give us different products, ketone or aldehyde. Internal alkynes, same product for both. Because internal alkynes, right, cannot be switched by Markovnikov's rule, right? Markovnikov cannot apply because you have an internal alkyne, you have secondary carbon and a secondary carbon, and so there is no difference in steric hindrance or carbocation stability between those two positions. So internal alkynes will always just give you a ketone product regardless of which conditions you use. So terminal alkynes different, internal alkynes the same.